Hello everyone, my name is Yingjun Du. Today I will present our work, EMO, Episodic Memory Optimization for Future Automated Learning. This paper is also joined by Jiayi, Xiantong, and Case from University of Amsterdam. So what is episodic memory? A category of long-term memory involves the recollection of specific events, situations, and experiments. For example, your memories of your first day of school and your first kiss and so on. So what's the effect of episodic memory? In our childhood, if we have learned the ballet, jazz, and tap, and when we learn a new dance, for example hip hop, we can recall previous episodes of learning ballet, jazz, and other dances, and then we can use the learning process of those dances in the memory to learn hip hop better. So, what's the effect of episodic memory in machine learning? For example, here in the meta training stage, we have different tasks. For example, the task number 1 is a cat task classification, and task number 2 dog cat classification. And actually, in the meta test tasks, we can use the most similar meta training task to learn a new test task. For example, task number 1 is similar to the task number 1, and then we can use the learning process of meta training task number 1 to learn the task number 1. And actually, episodic memory has achieved great achievements in the different learning. For example, the reinforced learning and the continual learning. And so, how to use episodic memory in future learning? So we can use the learning process of each task, which can be seen as the episodic memory, and then we can use the most similar meta training task to teach the test task how to update their model. For example, the meta training task 2 is similar to the task, and then we can use the learning process of task 2 to update the task parameters, and then we can use the support set from task, and with only a few step gradient descent by support set to update the model. So why using episodic memory in future learning? Because for future learning, there are limited training samples, and actually traditional gradient descent methods get trapped in their numerous suboptimal local minima or sandpoints. So if we just use the traditional optimizer, for example, the stochastic gradient and a momentum optimizer, it will get trapped in their numerous suboptimal local minima. So in this paper, we propose episodic memory optimizer. We first propose an external memory to store the gradient history gained from the past learning experiments for optimization-based meta-learning. And when learning a new task, we can find the learning process of similar tasks in the memory, which is used to help update the model parameters using limited training samples of new task. And last, we propose a memory controller to replace the tasks from the memory. So here is the overall framework of our EMO, and actually our EMO is a key value mechanism, and we store the key. We use the task repetition as the key of the memory, and we store the gradient of the different tasks and the values, and our memory controller to replace the training tasks from the memory, and we propose 3 different memory controller to replace the memory, and we also propose the different aggregation functions to update the parameters. Here we propose the mean aggregation, sum aggregation, and the transformer aggregation to update the model parameters. And here is the benefit of our episodic memory optimizer, and we can see that with EMO, And adding EMO improves performance independent of the meta-learning methods of datasets. And EMO speeds up the memo training and outperforms the other optimizers for future learning. And here we show the effects of inner loop steps, and the memo with EMO can reach convergence very quickly. For example, here step 2 versus step 5, and perform much better than our other optimizers. And last is the comparison with the state of the art. Equipping ARML with EMO results in the top performance. That's it. If you have any questions, please contact me. Thank you.